Hi, Stu Schwartz from MasterMathMentor.com. This is video AB21. The topic is Absolute Extrema, and it covers the AB manual, pages 131 and 132. This video is based upon the extreme value theorem. The extreme value theorem states that if f is continuous on the closed interval AB, then f has both a minimum and a maximum on that interval. These can be at the endpoints or any critical points where f prime equals 0 or f prime does not exist. There are tons of examples of the extreme value theorem relevant to everyday lives. Sitting in your classroom, there is a student who's taller than everyone, and there's a student who is shorter than everyone. There's a student with the highest IQ, one with the lowest. There's a student who will outlive everyone else, and sadly a student who will die before everyone else. When you buy a car, there is some dealership who is selling that car at the cheapest price than anyone else, and another dealer who is selling it at the most expensive price. During a year, there is a coldest day, there is the hottest day. The extreme value theorem is all around us. So this video concerns itself with finding an absolute maximum and absolute minimum on a closed interval AB. Absolute extrema, sometimes called global extrema, can also be relative extrema, sometimes called local extrema, and vice versa. For instance, on this graph, f of x equals x squared minus 2x minus 1 on the closed interval 3, 4, the point 1, negative 2 is the absolute minimum as well as a relative minimum. The point negative 3, 14 is the absolute maximum, but not a relative maximum. The graph to the right shows the function over the interval negative 1 to 4. There is a relative minimum at x is equal to 1 and a relative maximum at x is equal to 3, but these are not the absolute minimum and the absolute maximum. The absolute maximum occurs at x is equal to 1, while the absolute minimum occurs at x is equal to 4. So the absolute extrema occurs at the endpoints of the interval. A word about semantics. When you are asked to find relative extrema, you are usually concerned with the x value where the relative maximum or relative minimum occurs. For the left-hand graph, we would say that there is a relative minimum at x is equal to 1. But when we are finding absolute extrema, we have to be careful in examining what the question asks. If we are interested in the location of the absolute maximum or minimum, we are interested in the x value. But if we are interested in the absolute maximum or minimum value of a function, then we're interested in the y value. So in the graph to the left, we would say that the absolute maximum of f occurs at x is equal to negative 3, while the absolute maximum value of f is 14. In the curve to the right, the absolute maximum value of the function is 8, and the absolute minimum value of the function is negative 6. So we will look at the procedure to find the absolute maximum and absolute minimum value of f of x on the closed interval AB. We will do this by showing an example. F of x equals 2x to the third minus 9x squared plus 18 on the interval negative 1 to 5. Step 1 is to find the critical values of f on the closed interval AB by setting the numerator and denominator of f prime of x equal to 0 and solving. So we have f prime of x equals 6x squared minus 18x. Factoring into 6x, quantity x minus 3 equals 0, and x equals 0, and x is equal to 3. Step 2 is to evaluate each critical value of f on AB. So we look at f of 0, which is 18, and f of 3, which is negative 9. In step 3, we evaluate f at each endpoint of the interval AB. That is, we'll find f of A and f of B. Extrema cannot occur at open endpoints. So f of negative 1 is 7, while f of 5 is 43. We now have the candidates for the absolute maximum and absolute minimum. The largest of these is the absolute maximum, while the smallest of these is the absolute minimum. So the absolute maximum is 43, while the absolute minimum is negative 9. It is important to answer the question that is asked. Discern the difference where the absolute max or absolute min occurs, as opposed to what the absolute max or absolute min is. Where is the x value? What is the y value? So in this case, we would say that the absolute maximum is 43 at x is equal to 5. The absolute minimum is negative 9 at x is equal to 3. It is always beneficial to graphically confirm your results. Shown here is the graph of the function, and we can see that the absolute minimum is also a relative minimum, while the absolute maximum is not occurring at the location of the relative maximum. It occurs at one of the endpoints. Finally, realize that you can eliminate choices by using the first or second derivative test on the critical values. For instance, on the example we just did, if we had done some work to determine the location of a relative minimum and realized that it was at x is equal to 3, then it cannot be the location of the absolute maximum. In problems 1 through 8, you're asked to find the absolute maximum and absolute minimum on the given intervals. Typically, you're asked to justify your answer. I like to do the derivative work showing the candidates for the absolute max and absolute min, and then do my justification within a table where I show all my candidates and the values of f at those locations. Although not specifically asked for, I show graphs to confirm my answers. 1 is the easiest. We're given that f of x equals 3x squared minus 24x minus 1 on the interval negative 1 to 5. We start by taking f prime of x, getting 6x minus 24, and set it equal to 0. That gives 6x equals 24, or x is equal to 4. So there are 3 candidates for the absolute extrema. X is equal to 4, and the 2 endpoints, x equals negative 1 and 5. F of 4 is negative 49. F of negative 1 is 26. And f of 5 is negative 46. So the absolute minimum is negative 49, occurring at x is equal to 4. And the absolute maximum is 26, occurring at x is equal to negative 1. The graphic confirmation shows a parabola with the absolute minimum at the vertex and the absolute maximum at an endpoint. For a parabola, the absolute minimum or maximum must occur at the location of the relative min or max, which is the vertex. In 2, we have f of x equals 6x cubed minus 6x to the 4th plus 5 on the interval negative 1 to 2. Our first derivative is 18x squared minus 24x cubed. And set equal to 0, we get 6x squared times the quantity 3 minus 4x is equal to 0, giving x is equal to 0 and x is equal to 3/4. So there are 4 candidates, x is equal to 0 and 3/4, and the 2 endpoints, negative 1 and 2. F of 0 is 5, f of 3/4 is 5.633, f of -1 is -7, and f of 2 is -43. So our absolute max is 5.633, and our absolute min is -43. Shown is the graphical confirmation. Notice that at x is equal to 0, we have neither a relative min or relative max. We have an inflection point, and the curve just gets slightly higher than that at x is equal to 3/4. The absolute minimum is at an endpoint. In number 3, we are given f of x equals x squared over x squared plus 3 on the interval -1 to 1. We start with our derivative, which is using the quotient rule. We square the bottom, x squared plus 3 quantity squared, and upstairs we get x squared plus 3 times 2x minus x squared times 2x. This gives 6x over x squared plus 3 quantity squared, set equal to 0. We get x is equal to 0. The denominator cannot equal 0. So there are only 3 candidates, x equals 0, -1, and 1. When x is equal to 0, y is equal to 0. When x is equal to both -1 and 1, f of those values is equal to 1/4. So there is an absolute maximum at x is equal to both -1 and 1, and the absolute minimum is at x is equal to 0. The graphic confirmation shows that there can be multiple locations where an absolute max or an absolute min occurs. 4 reads f of x equals 2x over x squared plus 1 on the interval -3 to 3. Again, we use our quotient rule to take the derivative, squaring the bottom, and upstairs getting x squared plus 1 times 2 minus 2x times 2x. This gives us 2 minus 2x squared over x squared plus 1 quantity squared. Set equal to 0, we get x is equal to plus or minus 1. Again, the denominator cannot equal 0. So there are 4 locations for absolute extrema. X is equal to 1, -1, and the endpoints -3 and 3. At x is equal to 1, the value of the function is 1. At x is equal to -1, the value of the function is -1. And at x is equal to both -3 and 3, our answers are both -3/5 and 3/5. So our absolute maximum is 1 at x is equal to 1, and our absolute minimum is -1 at x is equal to -1. Our graphic confirmation shows that for this problem, the absolute max and min occur at the locations of the relative max and min. Now that we have the procedure down, let's show several problems that have some exceptions to the procedure. Number 5 reads 3x to the 2/3 minus 2x plus 1 on the half closed interval -1 through 8. Taking our derivative, we get 2 over x to the 1/3 minus 2. It is best to work this with a common denominator, so we have 2 minus 2x to the 1/3 over x to the 1/3. The numerator is equal to 0 when x is equal to 1. Our denominator is equal to 0 when x is equal to 0, and therefore the derivative does not exist there. So there are 4 candidates. X is equal to 1, 0, -1, and 8. At x is equal to 1, f of x is equal to 2. At x is equal to 0, f of x is equal to 1. At x is equal to -1, f of x is equal to 6, and if x is equal to 8, f of x is equal to -3. Our absolute min is clear at x is equal to 8, But this curve has no absolute max because in reality, x cannot equal -1. It's not part of the domain. So this curve has no absolute max. Now, the limit of f of x as x approaches -1 is 6. So this curve gets higher and higher with a limit of 6. But since it never actually gets to 6, there is no absolute maximum. The graphic confirmation shows that the graph has a cusp point at x is equal to 0. The absolute maximum is -3 at x is equal to 8. However, because of the open dot at x is equal to -1, 6, this curve does not have an absolute max. It gets as close as we want to 6, but never actually reaches it. Number 6 reads f of x equals 3 minus the absolute value of x minus 2 on the interval -2 to 5. From our previous knowledge, we know that f is a v-shaped curve which is not differentiable at x is equal to 2. So that has to be the only critical value. So there are 3 candidates, 2, -2, and 5. F of 2 is 3, f of -2 is -1, and f of 5 is equal to 0. So this curve has an absolute max at x is equal to 2 and an absolute min at x is equal to -2. The absolute max is 3, the absolute min is -1. As with parabolas, our graphic representation shows that in a basic absolute value curve, the vertex will be the point of relative extrema and also absolute extrema. In 7 and 8, transcendental functions get put into the mix for this procedure. 7 asks for the absolute extrema for f of x equals sine squared of x plus cosine of x on 0 to 2 pi. We take our derivative, getting 2 sine x cosine x minus sine x. We factor out a sine x times the quantity 2 cosine x minus 1 equals 0, meaning that sine x equals 0, and we have x is equal to 0, pi, and 2 pi. We have cosine x is equal to 1/2, and x is equal to pi over 3 and 5 pi over 3. So there are 5 candidates for absolute extrema. At x equals 0, f of 0 equals 1. At x is equal to pi, f of pi equals -1. At x is equal to 2 pi, f of 2 pi equals 1. At x is equal to both pi over 3 and 5 pi over 3, f of x is equal to 5/4. So we find that the absolute minimum is -1 at x is equal to pi, and the absolute maximum is 5/4 at 2 locations, x equals pi over 3 and x is equal to 5 pi over 3. The graphic confirmation for number 7 shows that the absolute extrema also occur at the points of relative extrema. In 8, we're told that f of x is equal to natural log of 1 plus x squared minus x on the interval -e to e. We take our derivative and we get 1 over 1 plus x squared times 2x minus 1. It is best to get a common denominator, so we have 2x over 1 plus x squared minus 1 plus x squared over 1 plus x squared. And when we put the numerator together and factor, we get negative quantity x minus 1 quantity squared over 1 plus x squared. Setting that equal to 0, x is equal to 1. So there are 3 candidates for absolute extrema. X is equal to 1, -e, and e. At x is equal to 1, f of 1 equals the natural log of 2 minus 1. At x equals -e, f of x is equal to natural log of 1 plus e squared plus e. and x is equal to e, we have f of x is equal to the natural log of 1 plus e squared minus e. So the largest of these values is the natural log of 1 plus e squared plus e at x equals negative e. And the smallest is the natural log of 1 plus e squared minus e at x equals e. Shown is the graphic confirmation of number 8. Note that the absolute max and absolute min occurs at the endpoints. The critical value x is equal to 1 turns out to be an inflection point. As we will see in the next two videos, many times in calculus we are asked to maximize or minimize a quantity. In these problems we found the maximum value of a function, but we can also maximize other types of expressions. So in this bonus problem we are asked to find the maximum slope of f of x equals negative x to the third plus 3x squared plus 4x minus 20 on the interval negative 3 to 4. In order to maximize our slope, we must first find an expression that expresses our slope. We will find this to be true in all of these types of problems. If we want to maximize our salary, we must first find an expression that expresses our salary. If we want to minimize our risk to COVID-19, we must first find an expression that expresses our risk to COVID-19. Once we have written our expression that we would like to have maximized or minimized, we take its derivative and set it equal to 0. So in this case, we have our slope, which we know is f prime of x, and that is equal to negative 3x squared plus 6x plus 4. We then take the derivative of the slope, which turns out to be the second derivative of f, getting negative 6x plus 6. We set that equal to 0, and we get 6x equals 6, and therefore x is equal to 1. So we have three possible locations for the maximum slope of our function at x is equal to 1, negative 3, and 4. We plug those values of x not into the function, but into the slope of the function, which is f prime of x. So f prime of 1 is equal to negative 3 plus 6 plus 4, which is equal to 7. F prime of negative 3 equals negative 27 plus 18 plus 4, which is negative 5. And f prime of 4 equals negative 48 plus 24 plus 4, which is negative 20. So we find that our maximum slope occurs at x is equal to 1, and the maximum slope is 7. The graph is a confirmation of our answer. We see the graph of f of x, which is decreasing, then increasing, then decreasing. It appears that the graph is increasing approximately on the interval negative 0.5 to 2.5, which means that the maximum slope must occur somewhere in that interval. We see it is at x is equal to 1. The second graph shows what we did algebraically. It is the graph of the slope, which is f prime of x, which is negative 3x squared plus 6x plus 4. We were interested in maximizing that slope, and we found that that occurred at x is equal to 1. When we plug 1 back into the expression for the slope, we ended up getting 7. In the next two videos, we will culminate our study of differential calculus with applications of max-min problems. These situations are all around us, like finding the quickest route to school, or by making the most money on something you sell, to getting the best possible grade with the least amount of work. So stay tuned.